Okay, I'm ready.
Great. Make sure I'm ready. Too many windows here.
Please let me know when I should do a slideshow.
Go ahead. You can do a slideshow now. We'll just start.
Okay, great.
Okay, great. Everybody, welcome to our Thursday seminar. Sorry for the little delay, and I'm glad to see the people are still with us. We've been doing this for a whole year, and I'm every Thursday. It used to be every Thursday at 4. Now it's every other Thursday at 4. And I'm glad to see our regular customers are there, and we are also in parallel, of course, on YouTube. And also every week we see somebody new, and so it's good to welcome people who are joining us for the first time. Very happy to have Dr. Nikku Madhusudhan from the Institute of Astronomy at the University of Cambridge give us our colloquium today. Nikku has had a checkered career. He started off very interestingly as an engineer in the BHU IIT, was an engineering graduate, went over to the MIT. He has a PhD from MIT, did postdoctoral work at Princeton and Yale, and then joined the Institute of Astronomy in Cambridge about 10 years ago. He has received many awards for his amazing work in the last over the last decade on various aspects of exoplanets. He was in the news even during his postdoctoral time. I remember, a lot of you would remember the Indian newspapers going gaga about the planet made of diamonds or whatever, or planet. It's wonderful. Some of these become wonderfully newsworthy. Nikku came to India to get the Vainu Bapu Gold Medal and gave a wonderful talk, which a lot of us attended, the Bapu Memorial talk at the Srinagar ASI, which is very memorable. And I'm sure today's talk will be very memorable too. Over to you, Nikku.
Thanks a lot, Shamak. It's a real pleasure to be here. I wish I could be there in person. I have visited IUCAA before and it was great. So I'm really glad to be here again, speaking to you all and share some views on the what we call as the frontier of the frontiers, is exoplanet atmospheres. So as you all know, exoplanet science is the major frontier of modern astronomy. And within that, the study of exoplanet atmospheres is even more of a cutting edge within that field. Now, 10 years ago, if you had even talked about some of the things that I'm going to talk about today, people would find it extremely surprising if someone said we'll measure chemical abundances of exoplanet atmospheres or all the kinds of things that I'm going to tell you about. But here we are today and have made tremendous progress just in the last decade, various observational advancements and various theoretical advancements. So I'm going to share my views on this particular domain. And at the start, I would like to thank you for inviting me to this colloquium, giving this opportunity to share with you some of the great things that are happening. So with that, let me just start. Let's say, yeah, so that's the broad outline of my talk. So I'll start with a very big picture for those of us who are not familiar with the field of exoplanets. I'll just give you a big picture on the motivation of why we are doing what we are doing. And then I'll spend a considerable amount of time talking about the latest results on exoplanet atmospheres from an observational point of view. What kind of data we're getting, what kind of inferences on atmospheric properties we're making, and so on. And then the last 20 minutes to half an hour of the talk, I am going to talk about implications of what we are measuring, what we are learning from the atmospheric properties. So I'll talk about two things that are two broad areas that are at the forefront of this field. And then I'll end with some future directions on where we are heading. Okay. So let's get started. So very standard slide here. If you boil down all the results of exoplanets as a field over the last couple of decades, the entire field is only about 25-30 years old. If we boil down all the results and ask what is the key takeaway, and it's that exoplanets are extremely common and extremely diverse in all the properties that we have been able to measure so far. Okay, so today we know planetary demographics pretty well, I would say, to the extent that we think almost every star should have at least one planet around it. Okay, so the occurrence rate, planetary occurrence rate, is nearly 100%. So that's the common bit. Now, if you talk about the planetary properties, and here I'm just showing you one example of planets from the Kepler mission, plotting the size on the y-axis, just radius, and the orbital period on the x-axis. So you'll see that if I showed you just the solar system planets, there is the, I hope you can see my cursor here. So that's the Earth, one Earth radius. And Uranus and Neptune are about 4 Earth radii. And then so those are the ice giants, and the gas giants, Saturn and Jupiter, are about close to 10 Earth radii. So if you took just the solar system planets and their sizes, then you would be led to think that there is a certain quantization in how nature forms planetary systems, right, in just the radius. It's very, very stark, this sort of quantization, 1, 4, 10. So for the longest time in planetary sciences, solar system planetary sciences, our theory of planetary formation has been somehow tuned to this kind of, not exactly this quantization, but to the properties that we see in the solar system, be it quantization in sizes or masses. Our formation theories are tuned to the solar system architecture of planets. But when you go to exoplanets, what you see that, and this has all happened just in the past 2 decades, the diversity just in one dimension, just that radius dimension, far exceeds what we see in the solar system. Okay, so there is no quantization. There is almost a continuum of planetary sizes and masses as well that we are seeing today, all the way from sub-Earth mass or sub-Earth size planets to super Jupiters. So you can begin to imagine the profoundness of what we are seeing here. Okay, so nature is much more complex, much more diverse than what we could be led to believe just based on the solar system architecture. What is more is that the planets between Earth and Neptune size, right, overwhelm the exoplanet population. So there are thousands of planets we know here, which are the most dominant planet category that we know of today. Yet the reality is that we have no analogs in the solar system. Okay, so these are called SubNeptunes. So towards the end of my talk, I'll talk about this emerging area of SubNeptunes. But you're already beginning to see the diversity here. So the punchline is that exoplanets are extremely common and extremely diverse. Now, if we know that just from a demographics point of view, just from planetary detections, why are there many more missions, space-based missions, TESS and CHEOPS are happening now? Plato will happen towards the end of the decade. Speculus is an example of a ground-based survey. There are many other ground-based surveys happening. So what are all these new planet detection surveys doing? The answer to that is that they're all, by and large, trying to find planets around nearby stars, and especially small planets, the subneptunes and smaller planets around nearby stars, so that we can characterize their atmospheres in more detail. So we know the statistics, but we want to understand much more about the planets themselves now. So all these facilities are trying to find those planets. So the question at the new frontier, which I'm going to spend the rest of my talk on, is how diverse are exoplanetary atmospheres. So this is the new phase we are entering. We know that in their bulk parameters, they're very diverse. Now we're moving to this new phase where we are asking how diverse are they in their atmospheric properties, and by inference, their interiors, their formation mechanisms, and all those things. Okay, So this is just a 101 slide on atmospheric remote sensing. And essentially what it is that, so you have this cartoon of an atmosphere, pressure is going down as you go up in altitude, and that's the x-axis is the temperature. And I'm showing you some typical temperature profiles of hot Jupiters, but you can scale these to other types of planets as well. But you can see examples of planets without temperature inversions. So if you look at the temperature structure in the Earth's atmosphere, for example, you see the stratosphere. We all know the stratosphere, right, where the ozone layer is. So beyond the if you keep going up, climb the mountain, the temperature decreases until some distance, some altitude. But if you go high up in the atmosphere and cross the stratosphere, the temperature starts increasing again. So that is called a thermal inversion. And that's because that's happening because of the ozone layer in the Earth's atmosphere. That can happen in exoplanets also and give you these sorts of temperature structures. This is just an example of a kind of atmospheric process that we're able to probe today in exoplanets. There are a whole host of other processes, clouds and hazes, vertical mixing processes, atmospheric circulation, chemical equilibrium, and photochemistry, atmospheric escape. All of these processes can be probed in exoplanets today with a whole range of observations depending on the wavelength. So if you are probing in the UV, you see the very top of the atmosphere where the UV photosphere would be. You see you can probe atmospheric escape processes, and then you go into optical, you can probe slightly deeper in the atmosphere, and by the time you get to the infrared, you're going to the real chemistry in the lower atmosphere where all the action is taking place. So this slide basically encapsulates the reality of the exoplanet atmospheric characterization today. Is that 10 years ago, if you told someone that we'll be able to do all these things in an exoplanet, even 10 years ago, it would not be believable. But today, it's the very clear reality that we're able to study all this process with a whole host of observations with various facilities. So again, in just the past decade, we have now made observations of at least 50 exoplanets in one band or more of atmospheric observations, order 50, actually even more, with various kinds of observations: transmission spectroscopy, emission spectroscopy, space-based, ground-based, and so on. Just to give you a sense of scale for how many planets we are talking about here. Okay, so we're getting into serious numbers, and I'll show you many more plots on population statistics very soon on atmospheres, not just planets. So let's get, with that sort of a broad overview, let's get to the main part of the talk. I'll survey what we know of exoplanet atmospheres today. So another 101 slide. I will, for the rest of my talk, I'll focus mostly on transiting exoplanets. There are atmospheric observations that are also happening for non-transiting planets and also directly imaged planets, but I won't have time to go into all those things. So I'll focus on transiting planets. And I'm sure you all know about a transit geometry where the planet's orbit is inclined in such a way that you can infer the planet passing in front of and behind the star. When the planet goes in front of the star, some of the starlight is coming through, is being absorbed in the atmosphere of the planet at the day-night terminator. You see this blue limb here. So that is where the absorption of the starlight is taking place. And that differential absorption, which means when the planet is not transiting, you see just the star. When the planet is in front of the star, you see a dip in the starlight due to absorption from the planet. So the difference between those two positions tells us what is the net absorption. Okay, that's what is plotted here, for example. And that net absorption divided by just the stellar flux is just this ratio of the areas, area of the planet disk over the area of the stellar disk. Except there's a slight subtlety here that transit depth, which is what it's called, that absorption changes as a function of wavelength. So if you see in some wavelengths where you expect water vapor absorption, then that blue annulus here will appear opaque and give you slightly higher absorption. Whereas if you see in a region, in a wavelength where there is no absorption from the atmosphere, you will see just the opaque disk of the planet. Okay, so I would like you to appreciate the difference here. that is a few hundred parts per million, okay, a few 10 to the minus 4. So the error bars here are a few 10 to the minus 5. This is about 20 plus 20 to 40 parts per million, these error bars on average. So you can see that we can make these extremely precise observations now to get this water vapor absorption peak in transit. And this is what is called as a transmission spectrum. Okay. And here you don't even need this red model to claim that there is an absorption here, which in this case is due to water vapor. So you can do similar, you can make similar sort of observations in secondary eclipse as well, which is just before eclipse, you're seeing this starlight and also the planet's thermal emission, and reflection if you are looking at in the optical. But when the planet goes behind, you're seeing just the starlight. So you can again do this differential technique and get the planet-star flux ratio in this case. And that has also been measured for numerous planets. Okay. And in between those two positions, we can get this thermal phase curve of the planets also. So these sorts of observations have now happened for numerous exoplanets, and I'm going to show you some examples of those. Now, before I show you more examples, it's always useful to remind ourselves where we were just about 10, 12 years ago. Okay, so these are early atmospheric detections on exoplanets, and you can see where only a couple of photometric points were available, and those were used to make water vapor or claim water vapor detections. And these observations typically have been revised after the fact. So the field was still like very much beginning. And in just about 10 years, look at the kind of observations we have today. And this is not even today, this is from 6 years ago. I'll show you more recent observations shortly. Okay, already by 2014, 2013, we had these sorts of observations. Thanks to the Hubble Space Telescope, there's an instrument called the Wide Field Camera 3 operating in the near infrared, which gives us this exquisite precision data. Okay, now these are all for hot Jupiters. These are giant exoplanets around very close to their sun-like stars. Now, fast forward to the more recent observations. I showed you just a couple of spectra here, but already by 2016, 2017, we were talking about populations of spectra. So here there are about 10 spectra of, again, hot Jupiters with water vapor absorption peaks and optical spectra. Okay. And similarly, we were talking about hot Jupiters earlier, but we also have now hot Neptunes and super Earths. We're going down the mass range of planets where we can detect these water vapor features. So by the time, until a couple of years ago, 4 years ago, we had made the first measurements of Neptune-sized planets. See, these are HAT11, HAT26 are slightly larger than Neptune, and you can see the spectral amplitudes very clear. But at that time, by the time we got to super Earths, this is a super Earth about 2.7 Earth radii, we had flat spectra. So the observations were still hard to come by just a couple of years ago for super Earths and mini Neptunes. So I'll come back to that topic, and those were all space-based observations. What I want to also point out is that we have been making major progress using ground-based observations as well. So these are some examples. Again, like some of this data are being revised and so on, but the basic spirit is that we have been successful already to detect several chemical features using ground-based transit spectroscopy. This is with VLT, an 8-meter telescope, this as well, and this is with HARPS, a 4-meter telescope, for example. Okay. So already, even with 4-meter ground-based telescopes, we are making reliable observations of exoplanet spectra. So for completeness, I'll also show some thermal emission spectra. These are all, again, with the Hubble Space Telescope, thermal emission measurements in the near infrared, where you're beginning to see population studies of these as well, as a function of gravity and equilibrium temperature and so on. So I won't go into these in detail, except to point the major theme here. In just the last 20 minutes, I have gone from talking about single objects to talking about tens of objects, which is where we were just a couple of years ago already. Okay. So the field is moving extremely fast. We are already into ensemble studies, and this is from a review paper for annual reviews I wrote just a couple of years ago, summarizing this state of the art. So you can see, again, population level spectra for several hot Jupiters in transmission and thermal emission. So where we could study trends. This is an old result, but it's still like the state of the art in terms of what we can do if you put a ton of HST time. This is with 60 HST orbits, and you can get this phase resolved thermal emission spectra of a hot Jupiter as it's going around the star. So these kinds of observations have already been possible 5-6 years ago. Okay, so this is old news, but I want you to know that we have done this, and it's doable today. So these are all observations of exoplanets, and you've seen that the observations are both extremely precise and numerous. We are doing this left and right for many, many planets. Now, what do we do with these observations? What can we learn about the planetary atmospheres themselves from these high quality spectra? And this is where comes this concept of atmospheric retrieval. It's essentially any remote sensing expert, even for Earth-based atmospheric remote sensing, would know this. It's basically you have your spectrum and you're feeding a model, an atmospheric model, to the spectrum and derive the parameters of the model, which are essentially the pressure temperature profile in the atmosphere and the compositions. Okay, or in the case of, if you look at Earth-based remote sensing, they do a much more detailed job of getting layer by layer temperature and compositional information. We do some simplifications for exoplanets, but the spirit is nevertheless the same. Okay, so you have the observed spectrum, you have parametric model, you do your radiative transfer, you have your atmospheric parameters here, and then you use robust parameter estimation schemes to retrieve these parameters, which are basically the atmospheric properties. There are a whole host of retrieval codes out there in the literature today. I had the opportunity to develop the first retrieval codes in the field. So that was my specialty back then, and already a decade ago we did that. And today there are numerous other retrieval codes, several from my group as well, more recent ones that are getting more and more precise estimates of atmospheric parameters from this data. So with that sort of a background of retrieval, now you can appreciate what I'm going to say here. So the concept, where we want to get to, is from these spectra, we want to translate these observed spectra into abundance estimates. Okay? So this has been going on for a while now. As I said, I've already worked on that 10 years ago for the first time. And in the last 10 years, our retrieval codes have gotten more and more robust, and the data has also gotten better and better. So we are able to translate observations like this into abundance estimates like this, which you're seeing at the top left corner here. Okay, so already 6-7 years ago, we were down to getting precisions of about 0.5 dex on average for the best quality spectra on the H2O abundances. Okay, and this is another plot showing abundance estimates as a function of planet mass. I'll show you more such plots. So I showed you this population level diagram just a couple of slides ago about 10 hot Jupiters. So in this work, for example, from my group and other groups also that have been trying to take these spectra and get their abundance estimate. So in this particular work, you can see that all these points, the blue points are abundance estimates. The error bars go between 0.5 to about 1 dex in water vapor abundance. Okay. So you're already beginning to see some trend here. I mean, there is no trend that is matching the solar system trend of abundance estimates, which is based on methane, but you're seeing that these abundances are consistently lower than what we expect based on the solar system. Okay, we'll see more of that. So that was just with transmission spectra, but if we put all these spectra together, this is from another review paper, if we put all these observations together, transmission spectra, thermal emission spectra, direct imaging, and all that, you see the data here. And again, you see that a number of these planets are significantly subsolar compared to what you would expect based on solar system metallicity trends. Okay, I'll get to metallicity trends later at the top. So a brief takeaway here is that most hot Jupiters tend to have, at least as far as we know, subsolar H2O abundances, lower water abundances than we have been expecting. Now, this is a very recent result, just from 2 years ago, less than 2 years ago, where for the first time we have done a population study of about 20 hot Jupiters, and this is just an abundance study based on transmission spectra for about 20, it's 19 planets. And we are trying to constrain water vapor abundances in all of them, these blue points you see here. And then some sort of a trend is beginning to emerge here. You can see this, the contours here are the fit to the blue data points, the blue water vapor measurements. The orange line here and the contours are the fit to the solar system metallicity abundances based on methane measurements. So you can see that the water vapor abundances for solar system are consistently, this trend is consistently below the solar system trend, but it keeps the general trend of abundances increasing with lowering mass. So that's interesting. So there is a significant depletion of water vapor, but there is still, the slope is still the same. On the other hand, for a handful of planets where we could measure sodium and potassium abundances, we are not seeing such depletion. So maybe what we are seeing here is some preferential depletion of oxygen and water relative to other metals in this atmosphere. So you can appreciate now we have went from observations to retrieving abundances to now beginning to say something about global metallicity trends of planets as populations, solar system planets versus exoplanets. And next I'll talk about how this is informing us about planetary formation as well. Okay, so that's the broad picture. I'll add one thing. I've shown you only metallicity abundance estimates so far, but what is fastly approaching, and the field is moving very fast on this, is that in addition to just water vapor measurements, we're also making high precision estimates of carbon to oxygen ratios. So then whether it is the oxygen abundance that is depleted or the carbon to oxygen ratio that is different, all these sorts of things we can answer with these kinds of observations. So again, like I made the first constraints on CTO measurements almost a decade ago, but right now the precision on such measurements are improving tremendously thanks to a whole host of observations combining, in this case, for example, HST observations in the near infrared, Spitzer observations between 3 to 8 micron for this object, and then we also have high resolution spectroscopy in the near infrared. This is just a model template. If you combine all of this, this is like the future that is unfolding in front of our eyes right now, hybrid retrievals with multiple data sets, multi-resolution data sets to get these precise abundance estimates. Okay. So I'll summarize the whole atmospheric inferences here by saying that we are detecting various molecules in exoplanetary atmospheres. We are making broad inferences of subsolar H2 abundances in several cases in the majority of hot Jupiters at least. And then we are inferring clouds and hazes in several objects. I didn't talk about that in great detail for lack of time. We're also measuring thermal inversions in several hot Jupiters. And what we're seeing are the beginnings of exoplanetary mass metallicity relations, which will help us understand something about planetary formation as a population. Okay. One key finding emerging from all of this, as I already mentioned, are depleted water vapor abundances. We're still trying to figure out why that is the case from a formation viewpoint, but this is where we are. Okay, so that was the first half of my talk as a broad summary of atmospheric inferences. I went a little bit too fast and I didn't cover all the topics possible because it's a huge field, but I hope I gave you at least a broad view and across one particular dimension of transiting exoplanet atmospheres and within that chemistry. Okay. At least that angle we have covered in sufficient detail. Now we will use what I've said so far, this chemistry, compositional estimates, to understand what we can learn about planetary formation in exoplanetary systems. So my goal in the rest of the talk is to highlight a few emerging areas in the field of exoplanet in this particular domain of exoplanetary atmospheres. Okay. So these are the two sub areas of one is on planet formation, another is the SubNeptune regime, which we're going to talk next. So when we want to understand planetary formation based on these abundance estimates, we make a broad assumption first, which is that when planets are forming in a disk around, let's say there's a planet forming around a disk, in a disk around its host star, the composition of the disk should be changing as a function of distance from the center of the disk. And the reason for that is that the temperature in the disk is changing as a function of space and time, right? As a function of farther you are from the disk, the cooler it will be, the longer you wait, the cooler it gets. So depending on where you are in the disk as a planet and how you are evolving through it over time, you accrete different compositions of material, planet forming material from the disk, okay, in gas and solids. Now, if you do that, then at the end of the day, the formed planet that we are seeing today, we are only seeing these abundance estimates. However, if we can make precise abundance estimates, let's say we get an inventory of carbon, oxygen, and other elemental abundance ratios, the big question here is that can we invert those abundances and try to reverse engineer the formation and evolutionary process of the planet during its origins. Now that's a grand goal, but that's where we are today in the field. It's a very difficult problem, and numerous groups in the world are trying to work this out. And I've listed various works that have happened in this direction, and I've also had an opportunity to work on some of the initial pathways to solve this or to address this problem. So I'll not go into too much detail. I'll just motivate this area a little bit for you to appreciate it. If we look at Jupiter in the solar system, this is this is a very old argument that I'm presenting for those of us who haven't heard this before. If you take Jupiter in the solar system and all the elements, you'll see that most of the elements, actually all of them other than oxygen, are significantly enhanced, 2 to 3 times enhanced relative to solar. So for example, the carbon to hydrogen ratio in Jupiter is about 3 to 4 times carbon to hydrogen ratio of the sun. So when I showed you this mass metallicity plot and you saw that trend, the solar abundance, the carbon abundance for Jupiter was about 2 to 3 or 4 times the solar C2H abundance. Okay. So all the other elements are like that. Now oxygen, until recently, the oxygen abundance was not known, but the Juno mission had recently made that abundance measurement, and that is borderline consistent with solar. It's got a large error bar, but it's slightly subsolar to slightly supersolar as well, but not as enhanced as these ones. Okay. But the point remains is that because all of these abundances are enhanced relative to solar, planet formation, Jupiter's formation theorists have argued in the past for this core accretion hypothesis, where you form Jupiter and you create a lot of planetesimals that will enhance the abundance of these various species, the metals, so to speak. So if you do theoretical predictions based on core accretion models, you come up with the same conclusion, is that for exoplanets, these are just theoretical studies, you expect metallicities that are significantly supersolar. See, this is Jupiter and Saturn, but you expect for exoplanets significantly supersolar atmospheric abundances and bulk abundances as well. And this is a prediction for Jupiter pre-Juno, before Juno, that if these are predictions for the oxygen abundances, or if you match all the other elements for the measured metallicities, you predict at least between 2 to 7 times solar abundance oxygen in Jupiter's atmosphere. But Juno hasn't seen that. Okay, so the oxygen abundance is depleted relative to other elements, even in Jupiter, in the solar system. So if you take strict predictions for core accretion models, they will tell you that atmospheric metallicities of giant planets would be significantly supersolar, and the oxygen abundances at least also have to be supersolar, which means the carbon to oxygen ratios should be subsolar. Okay, so that's the prediction. But obviously we've seen this plot before, that this trend of subsolar water vapor abundances clearly contradicts the second point here from basic giant planet formation models. And then the enhancement of other elements beyond or consistent with the solar system trend suggests that maybe it's the relative depletion of oxygen or water relative to other metals, which is the important factor here, and not the overall bulk metallicity abundance enhancements or depletions. Okay. So, I mean, this is a big topic, and I'm not going into too much detail here, but I'll just suffice it. I'll just make the summary statement that we are beginning, based on these abundance estimates, we are beginning to answer these foundational questions on whether we can constrain planetary formation process without chemical abundance measurements. This is one slide, because I mentioned about carbon to oxygen ratio before, I'll just put it here for completion. In that this water vapor abundance I showed you in the previous slide, this is all depleted, right? What we were saying. But you can deplete water vapor abundance in many ways. One is just lower the overall oxygen abundance. But the other way to do it is to just change the carbon to oxygen ratio. Okay, so this is the solar carbon to oxygen ratio of 0.5. But if you change it by a factor of 2 to C2 of 1, you'll see that the water abundance decreases by 2 orders of magnitude. Okay, so when we are seeing these depleted water vapor abundances, we are still currently unsure if that is because an overall metallicity or O to H ratio, the oxygen depletion, or is it because the carbon to oxygen ratio is just slightly enhanced, so it is skewing all the water abundance to lower values based on what the chemistry would suggest. Then your question is, then where is the oxygen actually going if all the water is depleted? It's going into this gray curve here, which is carbon monoxide. So you see, when the carbon to oxygen ratio is close to 1, all the oxygen binds up with carbon to form carbon monoxide, and there isn't much oxygen left for water. Okay. So that is where we are in the field right now, is to trying to understand whether the oxygen depletions that we are seeing are due to low metallicities, different C2O ratios, or what. And based on those, we are trying to understand, or as I said previously, recreate the formation conditions of these planets. And numerous studies are happening in this domain, which I won't go into. So the summary here is subsolar O2H ratios are suggesting various formation mechanisms, like discrete mechanisms, pebble accretion without core erosion, and so on. These are, I won't go into the technicalities, I just put the slides out here. And then supersolar O2H ratios, as I already said, can be predicted by correlation models, and you can achieve it by various paths. So the combination of O2H and C2O ratios are currently being used to probe these different formation regimes. Okay, so there are various avenues for future studies in this direction. Okay, so in the remaining few minutes of my talk, I am going to touch upon another area that is rapidly evolving, which is called the SubNeptune regime. You must have heard about this development that's happening in the field. If not, it'll be very apparent very soon. There are numerous results coming in this direction. So I'll sort of motivate what the deal is, what is happening on this frontier. So I've already mentioned that the low mass planets and small radii planets overwhelm the exoplanet population. Right? At the very beginning, I mentioned that. And this is just a pictorial representation of that. I've just plotted here the frequency, a histogram of all planetary radii of known exoplanets. You see this huge peak between the ice giants, Uranus, Neptune, and Earth. This is similar to the plot I showed you before. So these planets are interchangeably called subgiants or subNeptunes because these are all smaller than Neptunes. The importance of this is profound, is huge, because this range essentially spans the entire gamut of planetary internal structures, from super Earths or predominantly rocky planets to mini Neptunes, which is a little bit of rock, but a lot of ice and significant envelopes, hydrogen helium envelopes. So this on the right here is shown the mass radius curves for pure hydrogen. So mass versus radius for pure hydrogen spheres, for pure water at room temperature, silicate, which is rock, iron, and so on. And you'll see that these subgiants occupy this entire regime between those two extremes. Okay, I mean, they can't be pure hydrogen because then the radii will be over 4 Earth radii, but they can have significant fraction of hydrogen helium up to like 5–10%, but they can also be down here, which are purely rocky or very enhanced in iron. So they're abundant in demographics and vast in internal structures and possible internal structures and diversity. Now, why is this? We knew this population for a while now, but why is this becoming more and more interesting now? Is because latest surveys are discovering numerous such planets around nearby stars. So the TESS survey, for example, NASA's TESS survey, has discovered dozens of such planets around nearby stars, which means these planets, we can now look at their atmospheres. They're extremely conducive for atmospheric observations. So for the first time, we're able to probe the atmospheres of low mass planets and try to make some connections to their internal structures and possible formation mechanisms. Okay? And also, many of these planets are around nearby M dwarfs, which are cool, right? M dwarf stars are cool by nature, 3,000, 3,500 Kelvin temperatures, which means that the planets can also be cool and still be close in and transit. So this whole combination of factors means that for the first time now, it's an evolving story, we're able to characterize small and cool planets. We're able to characterize their atmospheres with current facilities. We would never have thought this would be the case even 5 years ago. So I'll show you some results on this frontier. So again, this is showing the subneptune frontier in different configurations. One peculiar feature, if you go to this, if you zoom into this histogram, is what is called as the radius valley. Again, I'm putting it here because you would hear about this on and off. This is called the radius valley in the subneptune regime, which means like the radius distribution is bimodal with two peaks, one around 2.4 micron, another, 2.4 Earth radius, another at about 1.4 Earth radius, and there is a valley in between. So how why these planets are sculpted into this distribution is sculpted into this valley is another major question in the field right now. It's an evolving story. As you can see, many of these references are from just last year. So this finding of this valley only happened a couple of years ago. So that is another huge theoretical avenue that's happening in addition to the observational feasibility of characterizing the atmospheres of these planets. So because we have limited time here, I'll just look at the case study of one such planet, K218b. They've only just less than 2 years ago, the first atmospheric observations were reported for this planet. You can see that the mass is about 8 Earth masses. The radius is about 2.6. This was an old radius, which was then later revised to 2.6 Earth radii. So it's a small planet, a subneptune, but HST observations were able to detect a clear water feature in this planet's atmosphere. This is a transmission spectrum, as I showed you before. Okay, so that was a very important result, is that we are seeing now that we can actually detect these things with the existing facilities, which we hadn't hoped in the past. Now, if you take the mass and radius of this planet, so it sits right here. So depending on which of those two radii, this or this you used, this is the more accurate one, the larger radius. Actually, like that was just 2 years ago, but the more recent value of radius, just as of last year, sits right on this boundary of this pure water curve. Okay, it sits right on this boundary. So from that, what you can infer essentially is that the planet's bulk composition can be made predominantly of water. Okay, it can be a water-rich interior. One other thing I'll state. Give me 1 second. Yeah. So if the planet is sitting right there, it's a degenerate set of solutions in the sense that it can be pure water, or you could have a predominantly water or rocky interior, but with a hydrogen-rich envelope on top of it. Okay, you remember the hydrogen-rich envelope went like this. The mass radius curve for pure hydrogen is above the water curve. So you'll need, if the planet is less dense than water, then you need a hydrogen envelope to explain the radius of the planet. So there are various internal structures that can explain the composition, the mass and radius of this planet. But what is more, you now also have atmospheric observations, as I mentioned. So this was a study just as of last year, published just about a year ago, actually, where for the first time, we combined the atmospheric observations and the bulk properties of the planet to see if we can come up with a holistic understanding of both the atmosphere and interior of the planet together. Okay? Again, this is something that we didn't think we would be here so soon, but we are. So from the atmospheric observations, we can, as I already said, we can make a clear detection of water vapor. These are coming from atmospheric retrievals, as I mentioned to you before. So we could clearly detect water. We could put some interesting upper limits on other species like methane and ammonia and so on. And then, as I already mentioned, this was the radius at that time, which was sitting slightly above the pure water curve. And there were several scenarios we could use to explain the interior composition of this planet. So you can see a largely rocky planet, but with significant amount of hydrogen helium, or like an Earth-like core with significant, like nearly half of water and a little bit of hydrogen envelope. Or you could have a predominantly water world, like 90% in water, and a very thin hydrogen helium envelope. So it's a degenerate set of solutions. But what is constant in all of these things is that a hydrogen-rich envelope is necessary to explain the observations, to explain both the atmospheric spectra and the mass and radius. These are just showing you cuts in various other, in the mass fractions of core versus envelope and so on. I won't go into the detail. Now, from that, what we have basically learned is that you are beginning with this atmosphere and atmospheric observations and the bulk properties. We're beginning to place constraints on the atmosphere interior coupling of low mass planets. Okay, so this is just a cartoon of a core, a water layer, and a hydrogen layer. And in the atmosphere, we're also able to model the temperature structure, the internal heat coming from the inside of the planet, the stellar radiation coming from the top. So we are able to do the self-consistent modeling of the whole planet, atmosphere, and interior at the same time. And from that, what happens is that now you can put some constraints on what the boundary between the atmosphere and interior would be. Now, again, this is too much detail to go into given our time here, but these red curves here show the loci of the boundary. This is the hydrogen, helium, water boundary, and the temperatures and pressures at that boundary, okay, for different internal temperatures. And I'll just pick a few points here. This, and this corresponds to the three cases I was talking about in the previous slide on the mass radius diagram. If I pick one case with the thinnest hydrogen helium atmosphere, what we find is that several of these solutions allow for liquid water on the water surface of the planet, okay, below the hydrogen helium envelope. There are several other solutions that fall in the supercritical water regime, which means the water will be too hot to be liquid. Okay? But the interesting bit is this: within this entire range of solutions, there do exist a number of solutions that allow for liquid water on the surface of this planet. Now that is exciting, right? Just from atmospheric observations and bulk properties, we are already beginning to place some interesting constraints on the surface conditions of this planet. Again, we are going into much more detail based on that. So this is another of my student, Anjali Piet, who does self-consistent modeling of radiative convective equilibrium modeling of these atmospheres. And we're able to explore a wide range of atmospheric parameters and systematically investigate now how the temperature structures of these planets change with various parameters, the internal temperatures, the radiation, the infrared opacity, and so on, and then put constraints on what kind of, let's say in this particular case, cloud properties can allow temperature structures that allow for liquid water at the bottom of the atmosphere. Okay, so this is just one example of that. We go into a lot more details in this paper, which was again published recently. Not only that, we can also predict that the thermal emission from these planets can be detected with the James Webb Space Telescope, which is due to launch very soon, later this year. And for the first time, we should be able to place observational constraints on the temperatures of the photospheres, and which in turn can put further constraints on whether these planets can have liquid water surfaces below their hydrogen helium envelopes. So that is what we are doing right now, pursuing a holistic approach for understanding super Earths and mini Neptunes based on coupling their atmospheric and interior properties with these various observations and internal structure modeling and so on. So that's it. So I've covered various aspects of exoplanet atmospheres and went into a little bit of detail into two emerging areas. And I'll end now in 1 or 2 minutes with these future directions. So these are all the areas I covered, I touched upon, but didn't cover in great detail. We didn't talk about atmospheric dynamics, non-Newtonian processes, habitable zones, and so on, or atmospheric escape. This is just to tell you that there is an enormous amount of complexity and detail that people are working on across the field. And all we have seen is a small snippet of what's happening, focusing on my own interest and what we are doing in our group, but also getting a general vibe for directions, upcoming directions in the field. Okay, so we already saw this big picture, so I want you to leave with this image of what we can do for exoplanets today already, and the future is with James Webb coming very soon this year, and with the future ELTs, the 40 meter class telescopes coming later in the decade. We are going to probe a wide range of wavelengths from nearly optical to mid infrared, all the way up to like actually 20 micron, 20 plus micron with the JWST, and numerous molecules. So if you saw how much we could do already today with existing facilities, just imagine how much we can do with JWST type spectra. So all that I talked today is about this small wavelength range. With JWST will open that entire range. So just I leave it to your imagination to see to think about what the next several years of exoplanet science would be like in terms of all the things that we discussed. Okay? So the future of exoplanet science, this is my last slide, is in two broad directions happening right now as we speak. One is detection of planets, small planets, around nearby bright stars. And another is the characterization of the atmospheres and interiors of these small planets around nearby stars. And in both these directions, there are major observational efforts happening. So these are space missions that are happening now and ground-based surveys. More space missions are about to come. And then the even uber cutting edge of the field is the atmospheric characterization of these objects. James Webb is scheduled to happen this year. On a longer term, you will have the ELTs coming first towards the end of the decade, and then towards the real end of the decade, 2028, 29, the aerial mission, is atmospheric survey mission, is going to look at several exoplanets as atmospheres as well. So broadly, the future of exoplanet science is bright, and there are major advancements happening in all these directions. So stay tuned for the next revolution to happen. Thank you.
Thank you. Thank you, Madhu, for this wonderful broad coverage of exoplanetary atmospheres. Shonok could not be here because of some meeting, but I'm there. And if you want to ask questions of Madhu, please raise your Zoom hand and I shall unmute you. Yes, Asim, please go ahead.
Yeah, hi. So maybe a basic question, but since you mentioned habitability towards the end, so I noticed that in one of the plots that you kept showing where you have size versus orbital period, if I try to locate the Earth, it looks like a pretty strong outlier.
Yeah.
So is this a real, I mean, is this a valid conclusion that I can draw from that plot, or is there something about the selection due to the techniques that I should keep in mind, and is it teaching us anything?
Yeah, it's mostly, I would say, selection bias because most of our surveys, all those plants I've been showing you are from transit surveys, which means there will be a limit on the period orbital period of the planet till which you can survey. So long period planets, at least if you're talking about Earth-like planets, 1 year orbits are hard to to detect. Like the transit probability is rare. You have to stare at it for longer. To confirm a planet radius in transit, there is a standard. You need a couple of transits to be sure, but that means it's several years for one planet, and missions usually don't last that long. And if they do, they don't detect as many planets. You see what I mean? So there is a detection bias. Now this Plato mission, one of its main goals is to find Earth-like planets or at large orbital separations. So those statistics will be more complete at that time. Does that answer your question?
Asim? Okay, I have to find him to unmute him. Okay, one sec. Does it answer your question, Asim?
Yes, yes. I have muted, so I was not able to unmute again.
Yeah, no problem.
Yeah, thank you. Yes.
Anand, can you go ahead?
Okay, it was a good talk. I'm wondering about these metallicity interpretations, because what we understand, the composition of our atmosphere is broadly decided by escape also, because that is standard question we keep asking our student, why there is no hydrogen in the atmosphere. So do you worry about that also when you talk about water depletion? Because if there is no hydrogen, you may end up with this equilibrium. You cannot assume solar composition there, right?
Yeah, so that's a very good question, actually. So these atmospheres are all of hot Jupiters. So they're all hydrogen rich. So that's a given. So
Okay.
it's the water vapor abundance relative to hydrogen. So it's the water mixing ratio that is depleted. So if you see how much water you expect in these atmospheres, it's typically for a solar composition atmosphere, it's typically 5 10 to the minus 4, 10 to the minus 3 at that level. Okay.
So continuing with this, if you take a ratio, for example, oxygen to carbon or carbon to something else, do you find a pattern between atmospheric composition and the stellar composition itself?
Yeah, so that is what I was showing you in that slide. I didn't specify it explicitly, that these abundances, that trend you saw of like depleted water abundances are normalized to their host stars.
Okay. You say solar, so I was wondering why solar. Okay.
It was my fault. I said solar in general. And that's also the reason for that is most stars are very close to solar metallicity, only slightly like about max a factor of 2 higher metallicities, but the abundance depletions we are seeing can be up to a factor of 10.
Okay.
So I use the term solar loosely, but they're actually normalized to their own host stars.
So ideally they should be same, right? Even I don't understand your argument about accretion, because accretion is coming from the protostar, which should have the same composition like everything, right?
No. So the assumption there is that the accretion is happening in the disk. So the primordial composition of the nebula and the disk are the same.
Okay.
But then, as I said, depending on where you form, some of this disk composition is going into ices and rocks.
Okay.
And if you accrete more rocks relative to the gas, then you enhance the metallicity because the gas is mostly hydrogen.
Okay. So it is condensation kind of problem in a loose physics sense. Okay.
Exactly.
Okay. Thank you.
Thanks.
Desh,
Yeah, enjoyed your talk. A related question to what you just discussed. Is it fair to now envision distribution of these abundances as a function of radial distance from the host star after having normalized for the host star properties? Is there a sort of general pattern emerging?
I mean, interesting question. That is the direction in which we are heading, but we are not quite there yet. The reason is all these measurements we are making are still for close-in planets. There's hot Jupiters or hot Neptunes, which are all very close or in close orbits to their stars. That means that there isn't much of a spread in orbital separation space in that population. But But we are getting there. Slowly, we are getting to farther and farther planets and getting their abundance estimates. So that's coming. And also, when you combine,
sorry, go ahead.
No, when
I
you
saw
combine,
encouraging spread in the orbital periods. I thought that might imply a range of radial distances.
Yeah. So the difference is that where I showed the plot of orbital separations, that was just for planets that were discovered in transit. But when I showed you the metallicities, this is for a much smaller subset of planets, only about like 20 planets where we have good metallicity assumptions, estimates. All of those are these hot planets in very tight orbits. And it's the temperatures that allows those sorts of good abundance measurements. So it's still a very biased sample.
Yeah, thanks. Look forward to this eventual filling of the spread. Yeah.
Absolutely.
So there were two questions in the YouTube. One by Kiran Mehta, who is asking, is the relative to Earth exoplanets plot for sun-like stars? Or is it for all stars?
Come again, I didn't understand the question.
I think what he's asking is it the relative to the Earth exoplanet plot? I mean, where you are plotting, I guess, the Earth radius.
I think, yeah.
I mean, the ratio of the radius to the distance, I guess.
Yeah.
Is it for all type of stars or only for solar-like stars?
Yeah, no, that's for all types of stars. It's coming straight from the Kepler discovery sample, so it's all stars.
Yes, and then there was another question by Akanksha Kandelwal. When a planet is not transiting, in that case, what kind of studies are used to study their atmosphere?
Yeah, very good question, actually. That I didn't go, I briefly touched upon the topic, but didn't go into great detail. But that's another, in terms of atmospheric observations, that's another like fast emerging area where you could do Doppler spectroscopy of the planet itself. So usually when you hear about radial velocity technique, you think about the star and Doppler monitoring of the star, the radial velocity of the star. But what we can also do is in high resolution spectroscopy, monitor the planet spectral lines moving as it is going in transit or around the orbit, depending on the configuration. So we could do basically radial velocity type measurements at high resolution for the planetary spectra and detect planetary spectral features as well. So there are various such observations happening in the field with high resolution spectrographs, both in the optical and infrared.
Right. Asim, you had another question?
Yeah. So maybe another naive question, but so given that the statistics are now improving and the numbers are going up, is it interesting to ask whether the solar system as a whole is special, or is it more typical, etc.?
Yeah, absolutely. That's a very valid question, and it's on our minds all the time. The question has to be posed in a way that is answerable by the observations we have at hand, right? So if you take like the solar system as a whole, then we don't have any analog of the solar system period. And that's mostly detection bias in my view.
Right.
Because even up to Jupiter's, we don't have like a complete sample, observed sample. But what we can do is take size as a metric, as a dimension, right? So if we say Jupiter-sized planets and look at all exoplanets that are Jupiter-sized under whatever orbital conditions, and say, are the compositions the same? Okay. Those sorts of questions we can answer now, and the mass metallicity plot, is one step in that direction.
But I was just wondering, because you mentioned that you are biased by looking at hot Jupiters in certain cases. Wouldn't there also be implications for solar system formation or exosolar system formation scenarios? Because if you have a hot Jupiter too close to the star, maybe the way it cleans up its surroundings is different than in ours, etc. So
yeah, so that is the inversion problem. It's a whole kind of worms, how you invert the abundances to get constraints on the formation. But you're right in that you can't directly map solar system formation scenarios to hot Jupiters because they're extremely different formation angles. What you can do is compare solar system Jupiter, for example, with directly imaged planets at large orbital separations. So there are a few that for which observations are being made like that. So that's a valid comparison. But there we don't have enough planets to make a statistical estimate like that.
Okay, thanks.
Sharbari, can you unmute and ask your question?
Yeah, hi, can you hear me?
Yeah.
Yeah, hi. Yeah, I was just wanted to ask you about the histogram that you showed about the abundance of sub-Neptune being higher. One would have expected to detect more bigger planets. So is that, I mean, what's the reason for having a higher population of sub-Neptune?
Yeah, so that was the main point of that plot. You would think that larger planets are easier to detect. In the solar system, we have many larger planets, as many or much more massive than the terrestrial planets. But that is what we are learning from the demographics, is that fundamentally in nature, small planets are much more numerous. So that's a fact. And it can't be just a detection bias, because as you said, detection biases work against that trend, in the sense that larger planets, you should see more of them, but we don't.
Sharbari, that was okay?
Yeah, I couldn't unmute myself. Okay, yeah, no, thanks. I think that answers it. But is that is there an understanding for why this is? I mean,
planet formation theories are beginning to say, and they have been saying for a little while actually, that just forming small planets is much more efficient. You need much less mass, and there are many more small stars which can again, which are continuously forming small planets and all that. So all in all, it's just emerging that planet formation is extremely efficient at making small planets.
Okay. Yeah, I had actually a related question. So does that histogram somehow relate to the masses of the host stars as well? I mean, is there or are these are they detected?
That's a very interesting question. I haven't seen like a cut. I'm sure there is a cut on histogram, per stellar mass. But it is true that smaller stars like M dwarfs host predominantly small planets. So it's very hard to find like giant planets around M dwarfs. So that may also be contributing to that distribution.
Okay. Thank you. Very nice stuff.
Thanks.
Desh, you had one more question, it looks.
Yeah. Tempted to ask about the gap that you mentioned in the mass distribution, which you said, is a puzzle. What is the present thinking? Or is there some?
Yeah, so it's a long story. There are multiple scenarios people are suggesting. One of which is, photo evaporation is sculpting some of these planets that are, sculpting the original distribution into this radius valley that we are seeing. There are other theories, basically. I don't know, like how much I should pitch on this, because it's a long answer. There is no short.
So what is the separation? What is the gap size, so to say?
Separation. So it's not in mass; it's in radius. That is
radius. Right.
The center is at like 1.8 Earth radii, and the peaks on either side are at 1.4 and 2.4 Earth radii.
Okay.
So there are multiple competing hypotheses to explain that gap, and one of the dominant ones is that photo evaporation from the host star is somehow sculpting some of the planets, getting rid of some of their envelopes and leaving where you see them today.
Yeah, thanks.
Okay, I myself had a question for you, Nikku. Naive question. We were all excited by this claim of life on Venus. So would you be able to claim at some stage life on an exoplanet?
So, I've been known to be too optimistic about this. My gut feeling, I'll just say, just witnessing how fast the field has progressed in the last decade, if I extrapolate it, I wouldn't be surprised if we, again, I'm being too optimistic here probably, but I wouldn't be surprised if we detect something in the next 5 to 10 years.
Right. Of course, the Venus claim itself is now slightly controversial, and
Yeah.
I guess. So.
Yeah.
Okay,
Yeah,
great.
I'm referring to planets in the habitable zones of their host stars and
Right.
with signatures that we know on Earth to be potential biosignatures. So those sorts of, like an atmospheric signature on a habitable planet around another star, mostly M star, I would guess it will be an M star because only those allow for characterization of small planets right now. I wouldn't be surprised if such planets would be claimed to have some sort of a biosignature detection in the next 5 to 10 years. Now, there is also a subtlety once you detect that signature, whether you can confirm it to be a biosignature or from some other source. That's a whole another story. But
yes. Yeah. Okay, great. I don't see any other question. And thank you so much for sparing your time and being with us. I hope you'll be able to visit us in person. There is no other way to clap. I can just clap for everybody. There is a Zoom hand clap also.
Yeah.
And thank you so much.
Yeah, thanks a lot for having me. I really enjoyed it. Thank you.
Yes. We had almost 70, 80 people at one stage, including the YouTube channel.
Right.
Thanks a lot, Nikku.
Yeah, no problem. Should I unshare screen?
We can unshare the screen, yes. Absolutely. Thanks, everybody. We'll see you back in 2 weeks' time.
Thank you. Have a good rest of the day. See you.